Mr. Nagy's Physics 11 class. We're continuing on with our study of waves. Just a quick review last day, as we've looked at types of waves already. I shouldn't say this was last day, but earlier in the unit, types of waves, things like transverse waves, universal wave equation, and so on. We're moved on past that. Last day's lesson specifically dealt with reflection, the law of reflection, and refraction of waves. That's waves traveling from one medium to another across some sort of a boundary. So the last two words here for our last lesson are diffraction, interference, just general properties of waves. So what is diffraction? Diffraction is the spreading of wave energy to fill the available. So here's a ripple tank, and I'm just going to generate some straight waves over here, and then there's a gap that they can go through, and let's see what they look like on the other side. Okay, one more time. We see that straight waves going towards there. I don't think the wavelength is changing at all, but the straight waves become circular waves. All that was happening here was we were generating some straight waves. I'll put those over here in yellow. Oh. So the waves, I guess they're blue. Going along here, constant wavelength, drawing these pretty well. Okay, they're moving in that direction right there. And as they hit this opening, okay, there's an available medium out here, and they don't just stay concentrated right here, trying to draw them at the same wavelength. Okay, they don't just keep moving in a straight line. And when we saw this in the actual ripple tank, of course, there'd be some reflection over here. It's tough to see. But all we're really concerned with is what's happening over here. And what happened is they kept about the same wavelength, and they curl around to fill in the available area. So a couple of questions to ask. What happens if we change the wavelength? What if the wavelength was shorter in between these? What happens if we change the opening? Make it shorter or a whole lot bigger here? What happens if instead of an opening, we put a barrier in here? What happens behind the barrier? So let's take a look at some of those examples. So this little animation here, a couple of things. And stuff we're going to consider as we look at interference is diffraction spreading around. I suppose waves might also want to spread out if there's sound waves spreading through the air around a corner. Or sight. People can't quite see each other. How come you can hear yourselves around the corner, but you can't see yourselves around the corner? So sound waves, if this guy is speaking, they tend to spread out an awful lot, okay? They spread right around the corner and the person can hear. We tried this in class, right? But what happens with sight waves? They don't bend as much. What's the difference between sight waves, light waves, I guess we would call them, not sight waves? Bit of a difference there. Let's take a look at, let's put a large object in here, and we've got some ripple tank sound or waves going through this tank and hitting this barrier in the middle of the tank. Again, there's some reflection going on back there that we're not too concerned with, but we can see these longer wavelengths bending in and really filling in back here. What if I make the object a little bit smaller? What's it going to look like in behind there? Can always stop this too, and really, again, we're not concerned with what's happened. There's some reflection going on back here, but what's it look like here? Okay, a very small object. Now we would say that there's more reflection or there's more diffraction around a large object than there is around a small object. The reason being, the waves here, they're basically straight. They filled in, but they don't have much of a curve to them. Whereas with a large object, too much of a dead area, but the waves have a lot of curve to them. Okay, they're not staying as parallel wave fronts as they did there. And next up, just having a look at diffraction, these straight waves going towards a slit. Okay, now I see the slit size, and I'm staying a little bit straight here and a little bit straight here. So let's notice how the gap size equals the wavelength. As the gap size equals the wavelength, the amount of diffraction increases, so the wave spreads out more. So let's get this thing running a little bit more. Okay, here the gap size is longer than the wavelength, and the wave coming through stays basically straight with just a little bit of a curve there at the ends. And now, with a smaller opening, curves and fills out, and it even gets over here a little bit more. So I think we could say that there's definitely more diffraction when it's a smaller opening than when it's a larger opening. Okay, so when there's a small opening for the same wavelength here and over here, small opening tended to have more diffraction. Okay, large opening, less diffraction. And diffraction is that filling around right there in particular. Okay, and when it's a large opening, didn't tend to be quite as much diffraction. Okay, and this was the other case there we saw in the ripple tanks where we had a small object and a large object. And we see here that with the small object, there tends to be less of that bending of the waves, so less diffraction there. And with the larger object, the waves are bending back on either side, so there is more diffraction in that particular case. And getting back to where we started this little discussion, talking about why the light waves don't bend around the corner, but the sound waves here do seem to bend around the corner. And as it says here, light has a very short wavelength, kind of exaggerating it there, whereas sound has very long wavelengths. So what happens is longer wavelengths tend to bend easier or more. That's a very poor drawing, but then short wavelengths, they don't bend around objects very easily. So light has a very small wavelength, and only small objects or gaps can affect its direction. Sound waves bend around objects of similar size to their wavelength, so the wall is similar to a wavelength. Okay, and now on to interference. Now, interference is going to occur when you have two or more waves traveling in the same medium at the same time. Okay, so here's what I'm going to do. I got this, the FET activity, the FET demonstration, and I set the tension here to high, and as we learned previously, that when there's more tension in the spring, the waves are going to travel faster. Perfect world of physics. I set the damping to 0, which means basically no friction. I make a fairly wide pulse, a fairly long wavelength, I guess that would be, and the amplitude, how far up I'm going to push it, I've set pretty good. So let's send a pulse. Pause it. Okay, so there's half of the wavelength because it's just a crest, and the amplitude from rest position up there. Now, what we've noticed with these is when we bounce a single pulse off a fixed end, it's going to come back as a trough. So what I'm going to do is, I'll play this, and I'm going to send another crest. Oops. Didn't want to do that. Let's pause that. I'm going to send a pulse and another pulse. Okay, so this one's going this way and that one's going that way, and they're going to meet here. And I'll play it for a moment and step these together. Okay, right there, they're in the same place at the same time. And then they go past one another. Now let's watch these things running. They keep meeting somewhere in around here. And if I pause them now, whoops, missed it. But I'll stop them there. Just step them forward a little bit at a time. It's like there's nothing there. Where'd the wave go? It's still there. They just cancel each other out for a moment. Okay, now what I'm going to do is send a pulse at a loose end. And when there's a loose end, it's going to bounce off, but a crest is going to come back as a crest. Hits that fixed end down there, it becomes a trough. Okay, I'm going to get this one just about to the end. I'm going to pause it. Okay, and I'll get it playing. I'm going to send another pulse, and that one's going to bounce back, and they're both going to be on the same side this time. Oops. There we go. That's where they're meeting in the middle. It's canceling each other out there. Meeting together. Takes a moment for them to catch up to one another. Okay, they're heading towards one another. What happens when they meet? Okay, they're both in the same place. Notice the amplitude there. Neither wave was nearly that high. And it looks like there's just one big crest, one big pulse, right? What happens is they meet and they add up to one another. Okay, normally the crest is only that high. When they met in the same place, they were both way up here, and down here the same thing if they're both troughs. So this is the last video we looked at there. This was a crest, and they were moving towards one another in the same medium. There's the rest position. There's the amplitude of each crest. And when they met at the middle, they added up to one another. This amplitude plus this amplitude right there gave me the amplitude of this. This is called constructive interference. Okay, this thing right here, in fact, would be called a maxima. Okay, where we've reached our maximum displacement from the rest position. And here again, this was the first case we looked at. There's a crest moving that way. There's a trough now moving that way. They are the same amplitude. And this one I stopped just before they were at the same spot. There's kind of the middle right there. And the reason I did that was, in fact, a moment later, if I had waited just a moment later, you'd see nothing. But they do pass right through one another. In fact, this crest a moment later would be down here, and this trough would be up here. They pass, but at the moment when they're both in the same spot at the same time, we see nothing. This is a case of destructive interference. Just abbreviate it there. This point right here where there's nothing is called a node. Okay, remember, we don't see this and we don't see this. We really see nothing. Now, what's this going to look like in a ripple tank? What we've got here is a ripple tank, and when I click, I'm going to create two circular waves. Okay, they fade out. I just created them for a moment or two, and we see this pattern here. Okay, the two circular waves, the same wavelength traveling in the same medium at the same time. Here's the same effect on the FET ripple tank. What we notice here is in particular, there's this region of these lines, and I'm not sure how well my cursor is showing up. I'll try and make it big, but they're kind of grayish lines. They're as if nothing's happening, and in between, we see these dark and these light areas. We're sending out concentric circles, these waves. Okay, I've got two sources, two taps stripping at the same time. Okay, and these areas right here, now we've got a special word for this kind of a interference pattern where we've got circular waves interfering and creating these dead spaces, and these dead spaces right here would be the nodes, and in fact the fact that they all fall in line makes them a nodal line. And this brightest spot right here, that would be a maxima, and this dark spot is actually a deep trough, that would be a minima. So here's that same ripple tank we were just looking at, took a picture of it. I've got two concentric waves forming at the same time. They're much neater there than I could draw them. And right here I've got a crest meeting a crest, if we assume that's crest. And when a crest meets a crest, just like up here, crest meets a crest, I get a maxima. I get a point of maximum disturbance. I'll just put max for maxima. And halfway in between the crests are troughs. Okay, so when a trough meets a trough, I also get a point of maximum disturbance. I don't have a picture of it here, but it would look something like here, and it would be exactly this inverted, these top two sketches right here. Okay, it's still a point of constructive interference. And this looked like a dark line, and this right here looked like a bright line, and again, a dark line there, and a bright line there, and they were moving, right, as we just saw in the ripple tank. Now, right in between here, I had, and I'll draw this in gray, there's a crest meeting a trough, and there's a crest meeting a trough, and there's a crest meeting a trough, and a crest meeting a trough, because the white line is a crest and halfway in between. These are, well, crest, trough, UGH, and they are nodes, pardon me, nodes. These here in the blue are minima, okay, maxima and minima. These are nodes, and the fact that they all seem to lie in a line makes it a nodal line. Now, because those lines didn't seem to be moving, or this pattern seemed stationary, we have a special word for this, and this is called a standing wave.